Okay, so we're on question 7H3 from the second edition of Statistical Rethinking. Here's the question. And so you can read it for yourself, and I'll just kind of summarize. But we have some data from 3 different islands, which are represented in the rows. And each island has 5 species of bird, species A through E. And the data is the proportion of whatever species inhabits those different islands. Okay? And so there's 2 things that we need to do here. And so we'll just take them in turn. But the first thing that we need to do is just to compute the entropy of each island's bird distribution and to interpret the entropy values. Okay? So we'll come back up and look at the second part after we do this first part. So here's my code. So what I'm doing is I'm taking, I'm just recreating this table up here, so that R can get a hold of it. So that's what all of this does here. Okay, it's just a data frame with the different species for the 3 different islands, 1, 2, 3, 1, 2, 3, 1, 2, 3. And now I'm creating a function called calc_h. Remember, H, capital H, is the symbol that we often use for informational entropy. We've already talked about what the definition or the formula for entropy is, and that's replicated here. Okay. And then I'm going to calculate the entropy for each island. And so the way I'm going to do that is I'm going to use the apply function. So the apply function says, okay, I'm going to apply a function. What function? Calc_h to this data frame, right, to this data along dimension 1, which is the rows, right? So what this is going to do is it's going to look at each row of my data frame, and it's going to calculate the entropy, okay? And then I'm just going to put that all together here with this last bit of code, okay? So everything except for the last column is just replicating the image up here. And then this last column is the entropy calculated for each island, okay? So now let's talk a little bit about this. So predictably, the first island has the highest entropy, okay? And why is that predictable? Well, it's because island 1 has evenly distributed species, or the proportion of the species is evenly distributed across all the species, right? And that is the criteria, or that is the situation in which we find maximal entropy. So it's not surprising that island 1 has the most entropy of the 3 islands. Okay? Now the other 2 have at least one, have a dominant species. Here, 80% for island 2 are species A, and on island 3, 70% are species C. Okay? And so that means we have major deviations away from this homogeneity condition of island 1, and so they have lower entropy. Okay? So none of that should be surprising. Okay, now the second part is we're going to use each island's bird distribution to predict the other 2, right? And so let me just parse that out. So we're going to pretend, say that I've observed island 1, okay, and I get these numbers, and I'm going to use that. So I'm going to use that information to predict what I'm going to find on island 2 and island 3, assuming that we're pretending that I haven't seen island 2 or island 3. Okay, and of course I'm going to be wrong in my prediction. Okay, and that's fine. And we're just going to note that how wrong I am. Okay, now. Similarly, we're gonna also pretend that I've visited island 2. I have its information, okay, and I'm going to use it as a model for predicting what I'm going to see on island 1 and island 3, assuming I haven't seen either of those. And then I'm going to note how wrong I am there, or expect to be there. Okay, so how wrong I am, what I'm calling how wrong I am, and using one model to predict another. We can kind of compute that with the KL divergence, right? And so we'll look at what KL divergence is here in a second. And so then we need to figure out which island serves as the best model, in other words, minimizes the KL divergence for the other 2 islands, okay? So let's go through that. So the first thing that I'm doing here is I'm making a function to calculate the KL divergence, okay, and the book gives the formula for it, okay, but roughly, if I'm using Q to predict P, where both P and Q are probability distributions, right? So maybe Q is the probability distribution found on island 2, and P is the probability distribution found on island 3. So I'm using island 2 to predict island 3 in that case. With each observation that I make, I'm going to be wrong by some amount, and that the amount that I'm wrong is encapsulated by the distance between log P and log Q, okay? And how often do I expect to be that wrong? Well, it's given by P, okay? So, because P is the actual distribution, so I'm going to be wrong I'm going to be this wrong P% of the time, if that makes sense, okay? So anyway, there's my function for calculating the KL divergence. And then I'm going to build an empty matrix here that I'm going to populate, okay? So this is all building a matrix, and it's going to have 3 rows and 3 columns, right? So 1 row for every island and 1 column for every island, right? Because I'm going to take island 1 and it's going to predict island 1, 2, and 3. And I'm going to take island 2 and it's going to predict island 1, 2, and 3, okay? And then I'm just going to start to use this for loop here to populate my matrix, okay? And all it's going to do is it's going to loop through, okay? It's just going to loop through island bird J. So it's going to loop through this row for whatever for row J. So it's going to loop through one of the rows, okay? And compare it with one of these rows, okay, or with another row, all right? And it's going to give me the KL divergence between that island and that island, between I and J, okay? So I'm going to run that, okay? And so here's my matrix, okay? So let's read this. So here I have island 1 serving as the model. So the rows are the model, and then the columns are the thing that is being modeled, the true distribution, okay? So here I have island 1 modeling island 1, and of course the KL divergence is 0, right? And similarly, island 2 modeling island 2, it's 0, and so on and so forth, okay? But if I go to this second entry here for island 1, so this is island 1 modeling island 2, and this is my KL divergence. Roughly speaking, it's kind of how wrong I expect to be when I use island 1 to model island 2, and similarly, island 1 modeling island 3, and you can go through the rest of them, okay? Now, this again is the entropy that we've already seen for the 3 islands, okay? And then this final column is the total distance of each island serving as a model for the other 2, okay? And we see that the total distance, the total KL divergence distance for island 1 when modeling island 2 and 3 is less than the other 2, okay? So in other words, island 1 seems to be serving as the best model of the other 2 islands, okay? And we might have predicted this. Why? Because it also had maximal entropy, right? It had the most uncertainty in its distribution. It was the most evenly distributed in its distribution, right? And so when it encountered deviations from what it expected, those deviations tended to be smaller when I assumed a uniform distribution over all of the different species, right? Whereas with island 2, say, when I'm using island 2 to model island 3, well, both of these have dominant species, and they're different dominant species, okay? And so that means that it's going to be very wrong very often, okay? And so we see a very high total KL divergence here, okay? So that's really the end of this question, but this will motivate later why we use a particular family of probability distributions coming from the exponential family. I believe that's coming up in the next chapter, or very soon anyway, if it hasn't already been brought up. And the reason that we tend to use probability distributions from the exponential family is that these are generally maximum entropy distributions. Okay, and so in the same way that the maximal entropy distribution here was really our best model, these maximal distribution, or these maximal entropy exponential family probability distributions tend to be strong models of things that we don't really know. Okay, so that is it for this one.